So welcome to our today's CAP seminar here at NCSA. So I'm very happy to introduce Tomo Matsumura, who's a faculty member at Kavli Institute for Physics and Mathematics of the Universe and the University of Tokyo. And he'll be he did his grad work on something near and dear to my own heart, a CMB balloon experiment, EBEX. I think that was the first one getting TESs, at least multiplex TESs, into a space-like environment. Yeah, so that was very exciting. And then he was a postdoc at Caltech for a few years, working mostly on Planck data. This is where Joaquin and I probably know him from. We were all down the hall for a couple years in there. Then he moved to Japan and worked you were at KEK, one of the particle physics labs, and then at JAXA, the Space Institute, and now at UTokyo and Kavli. And so he's going to tell us today about LiteBIRD, a near future CMB satellite experiment, we hope. So.
Well, thank you very much for inviting me. This is great. It's actually my first time coming to this town, so it's really exciting. Someone told me that it's just drive down to Chicago, so just it's good, and it is. And these days there's a Google map, and I can look up in 2 hours drive. And thanks to Jeff, and he introduced me. I was in University of Minnesota, so I know how the driving in the U.S. is like. So anyway, my first work trip from when I was a graduate student was from Minnesota to Chicago, actually. And I was told to go to Oregon from my supervisor, so okay, I'm going to go. And then he said, find the cheapest way to go. And I, instead of buying a flight ticket, I drove. It's just down next city, and then take 8 hours to drive. It's just straight all the way across Wisconsin. That reminded me. But it was nice to be here. And particularly, I thought it's very cold here. And so I brought, I call it as like a Midwest winter jacket. And it's just no use here. So it's a really beautiful day. And so thank you for inviting me. So for today, as I understand that with this audience, I have talk physics of the early universe using CMB polarization from space, LiteBIRD. And so what I'm going to talk about is overview of cosmology with a CMB, and a little bit of a focus on the space aspect in the past in the community. And then I'll introduce this space mission called LiteBIRD. And if time is allowed, I'll say a few words about some CMB activities in Japan. So I'll try to keep introduction short, but at the same time, I understand that you are coming from a various backgrounds. So always the picture to start with, this one, you have seen, I don't know, 1,000 times, zillion times, I don't know. But this is the very brief history of the universe. Here's where we are. This is the beginning of the universe. And this is the CMB, cosmic microwave radiation at the redshift of about 1,000. So this has been found by Wilson and Penzias in 1978. And again, this is, any cosmology textbook that you open up, this is something that you can read about. One thing that I always enjoy going to the original paper, particularly this one, is that this is the paper by them. Penzias and Wilson. It's just so strikingly short. The title is, I'm not sure if you can read it, but you start from here in less than 2 pages. And it says a measurement of excess antenna temperature at 4,080 MC/s, megacycle per second, megahertz. So 4 gigahertz, basically. And it's a so short paper. And that's 1965, Penzias and Wilson. So it doesn't say anything about CMB. It's just excess temperature. This is, what often people say it's just found by accident. Interesting to see that there's a accompanied paper to this, which is this one. One before this paper, this is just the end part of this, the previous accompanied paper written by DK and Peebles and Roll and Wilkinson, people from Princeton. They are the one who was actually looking for a CMB and consulted by this accidental finding from Penzias and Wilson. And so later on, I'll come back with the, despite the fact that these are the people who wanted to find this signal first, but it's scooped by Penzias and Wilson, but they continue their the effort and eventually leads to WMAP. So before getting to WMAP, I will let's say a few words. So after that, NASA COBE satellite launched in 1989, and there are two major discoveries. One is FIRES led by John Mather. This is a perfect black body. This is a famous one data point, and the fit perfectly well with a 1-fit parameter, which is the temperature CMB 2.7 Kelvin, and that is a big support evidence of a hot Big Bang. And then there's another measurement that's COBE DMR led by George Smoot, and this is the faint fluctuation, which is one part of 10 to the minus 5 level from the 3 Kelvin CMB, and that is fluctuation that's being observed, and that was the evidence of the CEDO structure. So by stretching this picture here, like that, and this is COBE, and after 10 years or so, again, this is from space mission WMAP, and this W is coming from the Wilkinson that I was referring earlier. And then another roughly 10 years after, this is Planck. This is now led by European Space Agency as opposed to the earlier two satellites led by NASA. And so you can see that this coincidence of the pattern, except the resolution that's being improved by Planck with the larger telescopes. So this is the oldest light that we can ever hope to see as a CMB. And then what does that mean for the red and blue spots? That in the end, we're trying to do physics, but to understand the physics, only the information that we can get is really light. Light contains intensity or wavelength or polarization. That's as much as we know. If you're working on the gravitational wave, that's another information that we start getting it. But really, photon is the one that we measure. But what we're trying to infer out of the photon is that the higher and lower radiation flux really refer to the higher and lower matter density at the last scattering surface. And so that's how we associate our measurement to the physics of the early universe. And so in the big picture, we're living in a solar system, which is part of the galaxy, which is part of a large-scale structure, which is seeded by the CMB. So this is even philosophically, very interesting way to see things. And then the question is now where that even seed is coming from. So this is famous 6 parameters describing nearly perfectly in this current lambda CDM cosmologies. So initial conditions and what does universe really made of, which is dark matter variance and the expansion rate and the tau, which is the optical depth measure of the first light, first stars. And we do have all the CMB information, but this is how do we infer more scientific context. We are not looking for a star galaxy, but it's really CMB, which is fluctuation on the full sky. So you take a Fourier transform, and since it's on sphere, so this is spherical harmonics, and you see a temperature power spectrum. This is a polarization power spectrum, E mode and B mode, and there are more information, but I'll skip that. And this is where the data and the theory meets, and it's hard to see it, but there's dashed line, which is the fit based on the prediction, based on the general relativity, and we can extract this information. And what's striking is that a popular public outreach sense what is the universe is made of. Dark energy 70%, dark matter 27%, the ordinary matter is 5%. That's typical message that you hear. And that's already scientifically also very interesting. But what's striking is that the error associated to it is this is a table coming from Planck. It's 1% or less. So this is often people call as an era of precision cosmologies. So in a way, it's all good and done, but the question is what's next. So that leads to the question in the time axis. And so currently there is still an unresolved question in our understanding of the universe within this so-called standard cosmology or ΛCDM cosmology, such as where the seeds come from, or why should the universe be flat, geometrically flat, or why do we see the same CMB between 2 points which can never be causal contact, or why do we not see observe monopole? So these questions, which is rather is a profound question, and these may have its own answer or solution to it. But it just so happened that the idea of inflation, which is a rapid expansion of the universe in early, just after the birth of the universe, that solved them all. So this is a theory or hypothesis, but this is a very leading hypothesis that's been around. And so if you take a cosmology textbook, you can find a chapter on inflation easily. In pictorial sense, this is the beginning of the universe. Now I'm focusing on this portion, which is easy to do on the PowerPoint because you just stretch that. And now I'm referring to really, it's not really a genesis of the universe, but it's just soon after the beginning of the universe and the expansion of that scale factor, basically. Now, often people refer inflation as the size of like a virus will suddenly stretch to the size of the galaxy. Unfortunately, we don't know such physics to explain the phenomena. And so we can ask ourselves, is inflation anything to do with the physics that we know today? And unfortunately, at least not to my knowledge. And no inflation postulated, no inflaton, the single field postulated by inflaton has not been found. And can we generate inflation within the current physics framework? So at least we can ask that. And so just to remind and bring you back to the very short history of the universe in different sense. So this is a high-energy particle physicist way of seeing the beginning of the brief history of the universe. This is Albert Einstein born, which is today. You can go back in time all the way with a unit of either time or energy scale. So, for example, recombination, the time that CMB is emitted is here, but so many milestones that can be associated here. This is another way of seeing the same, basically, a table with a little bit of carton, because this is Japanese people likes to use carton anyway. So this is gluon. This is photons and more. Basically, what it says is the beginning of the universe is here, but the four forces has split in a certain era. So the decoupling of the gravitation interaction is here, the decoupling of strong interactions, and decoupling of weak interactions. And so the bottom branch is often referred as a standard model, and the top one is basically we understand within the gravitational GR, general relativity framework. So with that in mind, for example, sorry, this is a very wordy slides, but for example, can we understand inflation within the physics that we know today? For example, introduce quantum correction within the framework of general relativity to induce inflation, inflationary cosmic expansion. This is one way to do, but however, there is still no well-established theoretical framework that justifies the introduction of such correction term. So there is attempt, and people are making it, but not fully consolidated. The other side from the standard model, high energy particle sense, Higgs particle is only scalar field in standard model, and therefore one possible approach is to consider whether Higgs particle itself could be an inflaton. However, the treatment of the interaction between the Higgs particle and gravity, basically the decoupling part, remain insufficient and posing technical challenge. And but whether one or the other, or maybe other solutions, or it could be a hybrid. So this is as much as within one slide I can say, but there is a smell of a new physics here as well. Now, when I say inflation, I have to dig in slightly more to associate between. We're now talking about the event at the beginning of the universe, 10 to the minus 36 seconds after the birth of the universe, which is quite early event that we don't reach so easily. And so how do we actually get to it observationally or experimentally? So first of all, I would like to establish the observable. So apart from the detail that I'm not going to get into it, but when it comes to inflaton, one can impose a potential, and you can draw various kinds of potentials as you like. This is one example, and there are certain conditions to meet in the current observational evidence, but it has to roll slowly, and at some point it dumped the energy. But the point is that so when I say understand the inflations, effectively understand the potential shape of this inflaton. That's one way to phrase it. Now, here, if inflation happens, then there will be some perturbation, which is a scalar portion and a tensor portion. Scalar is can be written as fluctuations, can be written in the power spectrum with some power law. So this is one way to write that. The tensor portion, which is gravitational wave portion, that's also you can write the fluctuation as this way. And the ratio of this power is called tensor to scale ratio. And this is effectively a measure of an energy scale of inflation. So that way, R is the number that I'll be tracing as the measure of energy scale of inflation experimentally. And without explaining how to measure, I'll just jump into to this. Currently, there is experimental upper limit on R by sub Keck, which is the telescopes on the ground from South Pole, and Planck, which is a space mission, that by combining those, currently we have a R less than 0.03 constraint. And in terms of the power spectrum, this is the so-called primordial B-mode power spectrum, which is responsible from the inflation. There's another curve that's written, which is coming from the weak gravitational lens in B-mode, which is not related to the inflation. So the key question is, can we constrain this primordial B-mode? And that amplitude is expressed as an R. It's a very small font. It just so happened that this particular curve is 0.01. But if the number is higher, then this curve goes up. This number is small, and this primordial B-mode part will go down. And then the current limit in the context of a tensor to scale ratio and the n sub s, which is this one, another important parameters. It is described in this contour plot. This might be slightly old version, but basically this is the meeting point between the data and the theory, again, for inflation. So the contour is coming from the measurement, and various points are corresponding to various inflation models. So then how do we measure? Coming back to this plot, it's just a PowerPoint stretched the beginning of the universe. we have been measuring CMB, which is a photon coming out from this last scattering surface. If there's an inflation, there will be a gravitational wave that's basically propagating through. So obvious way, conceptually, is to look for the gravitational wave itself. However, this is a very faint signal, and so in the future, hopefully we'll measure this gravitational wave coming from the inflation, but sensitivity-wise, it's yet to go some steps. On the other hand, if we can have the signal that is affected, the gravitational wave making some imprint to this CMB, and if we measure the CMB, then that is another semi-indirect way to probe this inflation, and that's where the inflation, the polarization is coming from. So for the sake of time, I don't explain, how the CMB polarization is generated by the gravitational wave, but you see two professors sitting here, and they're there to explain to you. So I'll leave that to them. So as a result, coming back to this plot again, this curve, primarily B mode, going up and down, we don't know where it is, and that's what we want to constrain. And so the signal is that we're looking for, which is the polarization of CMB. And that signal is, science-wise, is very exciting. And experimentally, we can probe really the beginning of the universe. That's one way to see in the time axis. Or you can reach the very high energy state, GeV, 10 to the 16 GeV, which is a gut scale. And so this excites from the particle physics community as well. As a result, there are a lot of telescopes in the world. And this is just a snapshot of some of them. So sorry, I couldn't squeeze all the telescopes as you might be working on. Some telescopes are in Chile, some telescopes in South Pole. There's some ballooning here as well, and then some telescope in Spain, Catalina Island, or Tibet recently, and there are some space missions as well. So why space? I'm going to switch to space, and then I'll talk about LiteBIRD after that. So why space? Space, because it's a full sky, you can access to it, and then there's no atmosphere. So single detector, the typical detector that we use, for example, transition edge sensor, bolometer, the sensitivity can be better because you don't have extra photons coming from the atmosphere. And also, CMB is not like a star or galaxy, but it's a fluctuation. And the atmosphere also fluctuates. So your signal and atmosphere is basically behaving very similarly. And so that degeneracy is always something that one has to fight with, but you don't have to deal with it, at least for the fluctuation coming from the atmosphere, if you observe from space. So that's another advantage. And finally, there's no limitation of the observational bands that you place, because if you're on the ground, or even from space, on the balloon environment, depending on the condition, there are some effect from the atmosphere. And so there are certain windows that you have to see through. Of course, just to be fair, space, it takes a long time to prepare. It takes quite a bit of funding. And so there are downsides, and you hope that you prepare everything as well and put it to the rocket. Hopefully, the rocket will launch with any accident and go to space. And once you go to space, you can't fix it. So all this, the other side that one has to take into account. Whereas on the ground, you can fix things relatively easily. So there are all these trade-offs. But traditionally in CMB communities, there are ground telescopes and balloons in space, and the space mission has been playing a crucial role, as summarized here. So I was talking about partially in the earlier part, co-BW map, and Planck. And the question is there any room for next generation CMB satellite to play a role? And that's where the main topic of LiteBIRD comes in. Okay. I should have said this, but if you have any question, please stop me anytime or later after the talk or even in this afternoon, I should be around. Okay, so LiteBIRD this is just a collection logo from the collaborations. There are many institutions. I actually don't remember how many institutions we have, but roughly 400 people coming from various places, Japan, North America, and Europe. Also, various backgrounds. CMB scientists, obviously, but some people coming from X-ray or infrared or high-energy particle physics from the science interest or technological synergies. And so this is the collaborations, and this is the flags of the scientists joining from each places. LiteBIRD is JAXA large class mission selected in May 2019 to be launched by this JAXA H3 rocket. So this is the one. And all sky survey 3 years from L2. And frequency coverage of something like 40 to 400 gigahertz with the 15 bands. The angular scale is something like a degree scale to less. So this is limitation of the size of the telescope. Excuse me. And then and the combined sensitivity, if you're familiar, something like a 2 microkelvin argument, which is a factor of 2 less than the lensing floor. This is another way to see it. CMB as a truly background, and this is the telescope. It looks like a ground telescope, but we see through it with many things. This is still CMB bit. Gravitational lensing. There will be a foreground, which I didn't mention. Atmosphere will not be there for the case of space, but there will be atmosphere. It's not, sorry, the galactic polarized emissions that we will see through. And so those are one of the important part. So LiteBIRD is targeting sensitivity level of polarization 30 times better than Planck. And the design philosophy is instrument systematic to be controlled and galactic foreground to be removed. And then lensing beam signal will be there. LiteBIRD doesn't rely on delensing. Of course, we're all happy to do a delensing with other experiment, but as a self-contained experiment, LiteBIRD will not rely on internal delensing. By the way, delensing, I didn't explain delensing. I mentioned delensing. Delensing is the signal. This is the weak gravitational lensing signal, which is converted from the E mode. And this is effectively cosmic noise that we have to overcome. And there are some certain techniques that one can measure this signal very well and sort of remove it and to probe even deeper. So that's the terminology delensing. And that's what we are not going to rely on. Okay. So I'll talk about what LiteBIRD can do in terms of science, and I'll talk about the configurations a little bit, and then talk about the status. So science-wise, generally L1 requirement is if the R is 0, the total uncertainty is 1 times 10 to minus 3. This includes a systematic error as well, and then the foreground residuals, all combined. If nature is kind and if R is larger, then we will try to have a 5 sigma detection from this. There are actually 2 bumps here. There's one bump which is called reionization. The other bump is called recombination. And it's obviously finding the signal itself is very important, but if the signal is large, it will be even nicer to be able to see the signal independently. And therefore 5 sigma detection of reionization and recombination independently. And so in terms of the constraint on R to the n sub s, if R just so happened that there is one famous model called Stravinsky model, which is the one that I was describing as the correction to the GR. In here, it's referred as the R square model, which is somewhere here. if that is the answer in the nature, this is a level constraint that we can make. If R is it happens to be 0, then this is the contour that we anticipate. And by the way, the blue is the current limit, and the green is what LiteBIRD will do. Okay, so that's the primary science that's been the LiteBIRD will be driven. But if you prepare an instrument for space driven by inflation signal, then there are more things that one can do. So, excuse me. For example, so B mode, primordial B mode for inflation, that's what I have been talking about. For example, I didn't explain what this shape should be. In standard inflation model, generally the curve is predicted like this shape. The question is where this curve is in amplitude. But if you address more the physics of inflation, one can come up with the other models which may have a different shapes to this curve. And so these are something that you can do if you observe the full sky and have a relatively large angular coverage. So that's one features. The other is that I didn't stress much, but and I'll explain in the next slide. So maybe I'll talk about this E mode aspect before other sciences. So let's see. I was only talking about E mode so far, but B mode so far. But there's another polarization signal called CLEE mode. And this is the signal that is, regardless of the inflation, CMB is expected to be polarized linearly as long as there is a density fluctuation in temperature. And that's measured in temperature already. So this is a guaranteed signal. And this particular low L bump is coming from the reionization of the universe. And this is the signal that is very hard to access from the ground. And there has been, just to be fair, there has been experiment attempting to constrain this signal from the ground as well as from balloon. But space mission is very ideal to constrain this well. And so, so this was actually one of the quote-unquote hallmark that Planck would have been done well. But there are a tiny bit of leftover hallmark from Planck. They have not constrained to the accuracy that we can ever hope to achieve on tau. And therefore, Planck current constraint is 0.007 or so. If you measure to the cosmic variance limited, then one should be able to go down to 0.002. So that is LiteBIRD sensitivity will definitely reach to the cosmic variance limited measurement of optical depth. And without waiting for 3 years, within 6 months or so, LiteBIRD will reach better than Planck sensitivity. Why do we care about this? I think reionization itself is very interesting. But on top of it, if it just so happened that if you do care about the neutrino mass, which is another profound the parameters that in physics, a neutrino mass is proposed without mass, but later on, because of the oscillation experiment, neutrino is found to be oscillating, and so there is a non-zero mass. The question is how much neutrino mass as a whole there is, and that will affect to the growth of the structure in of the universe. And in that way, by knowing how the large-scale structure is evolving over time, we can infer what the neutrino mass should be. But interestingly, there is a degeneracy in parameter between the reionization and neutrino mass. So all this great survey that will be coming up by CMB and also Galaxy survey, Spherics will be launched today. No, I think it's postponed to a week time scale. But those experiments will do, and LSST and many others, they can trace a large-scale structure, galaxy survey. We'll do a neutrino mass, but in the end, it will be limited by this tau. And so having tau to the cosmic variance limited will greatly improve our knowledge of the neutrino mass as well. So I think this is a very interesting sort of guaranteed signal that LiteBIRD can probe. So, and then other than that, for example, cosmic birefringence, which is another interesting topic, is the nature so that the time and the four-dimension time and x, y, z, is there any favorable directions, or are they the same? There are currently 3 sigma indication of a 0.3 degrees rotation between CMB traveling all the way to here today. And so 3 sigma is it's not sufficient enough to claim as a detection, but I think this is very interesting to in coming years. This is not just for LiteBIRD, but on the ground there will be a measurement, and so things like that can be done surely by LiteBIRD. Also, SC effect, constrained primordial magnetic fields, some anomalies, galactic science. All these things can come from LiteBIRD as a byproduct. So in other words, to say is that if you have a very high precision millimeter wave full sky map available somewhere on the website, and people can download and do a science for yourself. So that is another opportunity, which is different from going for R and try to get a single number, which is another element of this experiment. But I think there is so much value to learn about our universe in the way that you like, with such a map available in the millimeter wave. So having said this, and without just to see a time, this is very brief overview of what the LiteBIRD is like and what the LiteBIRD was like, and I intentionally use a past tense, and I'll explain that later. So first of all, LiteBIRD will go to L2, and the spin strategy is, if you're familiar with WMAP, more like that. The particular parameters are very different, so different in the way that it's just a different, but more or less it's a similar. It's basically a spinning top like at L2 to cover full sky. So this is the N-hit map after 3 years of survey. Try to be as uniform as possible, and basically observing 3 years. The spacecraft overview. So this is the part that I will be referring as currently we're trying to further optimize the mission configuration. So this is the one that's latest, that's being out, and there are ongoing studies. So what will come out in the end, this is to be seen. But covering the 40 to 400 gigahertz, 3 telescopes here, and TS's focal plane at 100 millikelvin, polarization modulator. Entire telescope is cooled down to 5 Kelvin. Detector is a combination of one coming from Berkeley, if you're familiar with, and the one from NIST. So a combination of CNES antenna and OMT coupled detector. And then so yep.
Sorry, the old design was 2 focal planes for each camera, right? So now it's the Planck model?
Okay, so this is a design a year ago, and this is how we proposed. And so 3 telescopes and 3 focal planes. 2 focal planes are TS CNES lenslet, and then higher frequency one is OMT, feed horn coupled, the NIST one. And both are read by the frequency domain maxing readout. But then, without waiting for the later slides, we're trying to see whether we can combine as a single telescope, because 3 telescopes with a 3 focal plane, that's already complicated enough to achieve. And also detector-wise, we're leaning towards the OMT feed horn couple fully populated single focal plane. Now, how to this is a part of the year-long study, which we are in the middle of it. Okay, and telescope has to be cooled, and detector has to be cooled, and so there are a bunch of cryogenics that goes with it, but I'll skip that. So then, speaking about the current status, so LiteBIRD went through this thing called a mission definition review, which is the very beginning, the gate to be a project. And we went through that, and that was successful, and that was the instrumental configuration that we showed earlier in the previous slide. And then it just so happened that KK is the one that was responsible for the focal plane detector. Originally, the US was planning to procure the detector part, but due to the funding reasons, they are not going to be able to do a full commitment. And so we are trying to re-optimize our configuration in such that we'll have a way forward. And so there has been a lot of discussion how to optimize it. Actually, for example, part of it is, for example, 3 halfway plate on a single each telescope. This is already for space mission, something spinning at the cryogenic temperature for 3 years. That's already quite a bit of a commitment to make. And so this is an opportunity to revisit, for example.
Have a question?
Yeah, can you say why you need a halfway plate since there is no atmosphere here? So why do you need a halfway plate given that there is no atmosphere?
Right, okay, thanks. So that's a great question. So yes, no atmosphere, but then no atmosphere means no one-over-F fluctuation. Then we still do believe that there will be some one-over-F, which may be coming from the readout, or thermal fluctuation, or somewhere in the detector chain. And Planck, for example, have seen 1/f about 100 millihertz. That just not. And so, so the question is, can you overcome with your spin rate, or have something like halfway plate? And so there is a trade-off here, and 1/f is one of the interesting things to work on, because in the end you don't know what will limit the 1/f, and it's very hard to come up with a model and say that this is a guaranteed 1/f level. And so to ensure that we are, and still we were, and we were still thinking the halfway plate is good. On the other hand, hardware-wise, halfway plate is another tricky device to bring to the space. So there is some trade-off that we're putting in. And also, it would be nice if you can just spin as fast as possible. And that's now with the freshman physics. Now we have a spin with a precision, and we have certain amount of mass and so on and so forth. And that leads to how many reaction wheels that you have to bring in and how much power that it takes. And so it's not as easy as, I mean, it's no gravity, it's just something's sitting in space. It seems to me it's just give a kick and spin fast, but not as easy as we thought it would. And so spin rate is limited. So these are the kind of trade-off that we're going through instrumentally and also with a lot of simulations. So so that is the revisiting the design phase, and also procurement plan is a current phase. And also, this is an opportunity to revisit the challenge in design anyway, and try to produce more margins. Also, this is the opportunity to learn what the technology is available from the community. There is a lot of heritage on the ground. Also, balloon is obviously a very great platform to raise a TRL, technological readiness level. And so this is what's happening. And right, so there will be a review later this year, so we're preparing for that. And because of this so reformation, unfortunately, I now take the PI roles, which is quite different from the usual professor job. But so if you have any official questions to LiteBIRD, I'm here to answer. But I'm speaking here as a scientist and try to be frank. I'm not here to do any politics here, so feel free to ask anything. Okay, and then finally, synergies between space and ground. So there has been a lot of efforts okay, I don't know what message I'm trying to relay because depending on whether you're a student or postdoc or faculty, you have very different views to CMB experiment. When I was a graduate student, I was working on the balloon experiment. I was sent to the New Mexico, that's where the balloon launch site is, and basically stuck with 5 graduate students. Professor has to go back to the university because they have to teach. And so 5 students are talking constructively, destructively for 2 months, quite dense time. And it's fun, I learned a lot. But those days are sort of gone. Now we have, for LiteBIRD, 400 people, even arranging the telecons is a nightmare. Simon's Observatory and the CMBS4, I don't know exactly how many people, but we're talking about, a few hundred to close to 1,000 people getting together. So it's a big community, and the experiment itself is big. And so I think it's nice to be able to think about the future in more collectively instead of sort of like, oh, I do this, I do that, and you just get funding and do it by yourself. And by thinking about it, I think it's very important to think about the synergies between the space and the ground. And with no surprise, without even getting to the next slide, I'm actually going back to the slide. This is a slide that I was showing earlier as a current limit on R. This is a bicep kick and Planck. This is actually, as a hindsight, bicep kick does their own things. I was part of the member at some point. Planck has their own aim, and they did that science. In the end, they combined the data together as a community effort and produced the current best limit. Now, when we look at the future, surely each experiment has their own self-contained science to aim to, but at the same time, it's good to have a brain exercise to see what, as a community, to put things together. Of course, we're using tax money, or some of the money actually now coming from private funding. But so in the end, from taxpayer point of view, your experiment and the other person is experiment, maybe they don't like to each other, but it's good to combine. The question is there room for optimization, or is there any preparation one can do? So that bit, at least from the space point of view, the spacecraft has its own size limitation, the mass limitation, so we can't really bring the large dish telescope anyway. The big dish telescope is really the game from the ground. So what you can do is, sorry, I should have put this slide earlier, but this is to explain this weak gravitational lensing effect, which is E-mode polarization in CMB altered its path, also polarization angle, about 2 arc-minutes or so with a coherence of 2 degrees, and that's where you produce B-mode. This is one way to learn about this large-scale structure. So this is what I was referring as a contamination for the inflation, but we can do de-lensing. So for example, advantage of space is, as I said, it's a all-sky survey with a good sensitivity and no atmosphere. But L range, or the angular scales that the space can probe, is as much as L of 200, like degree scale basically. Beyond that, that's really a role for ground. And so the question is, can we be complement each other in this angular scale range? And that's where we can appreciate this delensing. Similarly, high-frequency observational data from space can help remove the foreground emission contaminating to the ground-based data. So that is exactly Bicep, Keck, and Planck are working together. So that is another synergies. And that's why, for example, LiteBIRD team has an MOU with CMBS4 team to study this kind of synergies, but I think this can be extended even more. So put this into a bigger picture back again. So NASA, COBE, WMAP, and Planck, there has been a great effort, and also there has been quite a bit of a development from the ground. And sorry, I didn't list maybe your favorite experiments, and balloon surely is a part. The ground effort will be extended to Simon's Observatory and CMBS4. And along that line, if the LiteBIRD can be the next generation missions, then the question, what are the synergies? So that's what I was referring to. And even it's fine for some mission like a LiteBIRD in early 2030s can be a stepstone for even the future. My time scale is different from your time scale as a student or postdocs. So there has been, for example, idea of a comprehensive B-mode mission, like a NASA probe mission proposal PICO. This is even to do more from space, or spectral distortion, which is a whole other science that I do not have time to talk about. This is also another interesting science to be done. Or even if you extend even farther, gravitational wave interferometer, like from space, to really look into this gravitational wave aspect from the inflation. So by having said this, I think I'm running out of time, so I'll skip that to what I do in Japan. But just to summarize, so LiteBIRD is the JAXA mission for go for B mode, and okay, it's just so wordy, so I'll just leave it here. If you want to read it, please. Okay, thank you very much.
Thank you, Tomo. And I apologize, I meant to give a list at the beginning of the many CMB experiments you've worked on and technologies you've worked on. And the thing I left, that I didn't actually know you were LiteBIRD PI. I would definitely have included that, but I'm clearly a few months behind. Okay, questions?
We can talk more about this, but what are the current plans for detectors?
Right. So if I have just free to choose, then we're going to develop the detector in Japan and blah, blah, blah. But it's just, this technology has been so much matured in the US. And so obviously, if that was the original idea, NASA MO framework turned out to be not an opportunity, the available opportunity to join the international projects. So that door has been closed. So it's not really so much about the technology issues in terms of the US, it's really a funding opportunity. And so this is something that I have been exploring. There has been also an effort to see the European side can come up with the solution. They have not done so much of millimeter wave detector development, but there has been, interestingly, spike effort with a TS, and also Athena will be coming up. So X-ray collimator technology is there, but not millimeter wave. So there are bits and pieces, but never been put together for millimeter wave, and people are trying to do R&D. That adds extra a year or two, which is a downside, but that's another effort. What came out to be a potential solution, we'll have to see it.
Yeah, can you say how do you get the neutrino mass constraint? It cannot be internal to LiteBIRD, right? The neutrino mass constraints?
Yes, so right. Neutrino mass, what did I say? Yeah, so, okay, sorry, I don't have a number for neutrino mass, only from LiteBIRD. This is all combined with other tracer.
Okay, so this is like BAO or something?
Yeah, so
Okay.
sorry, this is very small, but it's with
yeah.
DAISY or LSST with a CMBS4.
Okay, okay.
And different contours with Planck or with LiteBIRD.
So is the primary source of LiteBIRD's power in constraining tau here?
Yes.
Okay.
So how hard is it to measure the reionization bump in BB with foregrounds? Is it similar complexity as EE, or is it harder?
How?
The reionization bump in BB just seems like EE is pretty hard given foreground stuff, and I can't decide if BB is going to be easier or harder. Or the same.
I see. Okay, so for example, so I can talk about a lot of simulation effort that's happening based on the what Planck has measured for the foregrounds, and there are various levels of complexity that we can assume, but that's all assumptions. But first of all, to make sure that I deliver properly, Planck EE was not fully cosmic variance limited, not because of the foreground, but it's limited by the instrument systematics. And so if that is not there, then I think there are enough component separation methods being around to remove that, at least for reionization. Now, what I do care is that then how complex the foreground in the end. There are a lot of complex models that one can come up within the error of Planck. And there has been a debate about some are physically reasonable, some are too complex. There are some external measurement, including one from SPIDER, indicating the level of complexity. So at that point, it's a bit hard for me to, okay, there are always a numerical simulation study that we're running to see how well we can do. If we are talking a very complex model that one can possibly coming up, then constraining the reionization bump of B mode is going to be not as good as we would hope for it. So I wouldn't claim that LiteBIRD will do everything regardless of the component, the foreground assumptions. There will be some line that we have to draw. And the other aspect is coming back to this halfway plate aspect, which is 1/f. And so 1/f will kick into the low L, and that will be another tricky part. And so this is really ongoing study.
Given the time, I'm going to suggest we thank Tomo and conclude, and you'll be around for some of the rest of the afternoon, but mostly over in Loomis.
Yeah.
So, thank you.